Hi, I'm Jie. Today I'm going to tell you all about our work on active storage systems. Recently, there are two emerging trends of system design. One is resource disaggregation, examples of which are disaggregated storage and serverless computing. Following this trend, system designers try to decouple the storage resource from the computation resource. On the other hand, we have another trend of storage-side computation. Following this trend, system designers try to utilize the computation capabilities on the storage side, and examples of which are SQL user-defined functions and Redis modules. And we observe that these two trends are diverging. On the left, the data is being moved back and forth between the storage nodes and the computation nodes, whereas on the right-hand side, the data remains in place and the computation is pushed closer to the data. Let's take a look at an example. If we design a system using the ship data approach, data would be shipped, the data would be moving back and forth between the application server and the storage server. And in this case, the storage server often acts like a key value store service, exposing a key value API. On the right-hand side, if we design a system using the ship compute approach, we would move the application logic into the storage server. And the storage server in this scenario would behave much like an RPC service, exposing an RPC API. And these two diverging approaches has its pros and cons. If we choose to ship data, we would have the benefit of resource disaggregation, such as flexible provisioning, elastic scaling. However, we would have to suffer from networking overhead because we are moving the data in between the servers across the networks. That would result in more networking traffic. And sometimes the execution of a single request would result in multiple network round trips, and this would inflate the request execution time. On the right-hand side, if we choose to ship compute, we would alleviate these network round trips because a single application request would always be corresponding to one RPC request. And we would not have to, we would have less network traffic, and we would not have the data marshalling, unmarshalling overhead because we are not moving the data across the network. However, if we use the ship compute approach, the storage server can get overloaded when the application is a compute intensive one. So really what we see here is that there's no one-size-fits-all solution. And each approach has its own fitting scenarios. Then a natural question would be, would we be better off if we combine these two together? So we conduct a measurement using a synthetic workload with configurable computation time and networking round trips. And we generate three classes of workload with different computation intensity, light, medium, and heavy. And we measure the throughput achieved at a specific latency target. And the result is shown as this. As we can see, for a compute-intensive workload, the ship data approach is better than the ship compute approach, whereas for a non-compute intensive workload, the ship compute approach would be better. And next, we combine these two approaches together by executing a fraction of the request using ship data approach and the remaining fraction using the ship compute approach. And we perform a extensive parameter sweep across different configurations of this fraction. And we find the highest achievable throughput for each individual workload, and we plot them as this. So as we can see, if we combine these two approaches together, we indeed can achieve a higher performance. The intuition behind this is a straightforward one, because when we are combining both approaches together by executing the request, a fraction using one and the remaining fraction using the other, we are essentially being able to use both CPU on the application server and the storage server. Therefore, we have a potential to achieve a higher throughput. However, a new question would arise: how do we achieve this optimal, and how do we find how much to what fraction of the request should be executed using the ship data approach, and what fraction should be using the ship compute approach? And especially, how do we do that when we don't know about the underlying workload? So we propose Kayak to solve that problem. Kayak, at its core, is trying to maximize the throughput under SLO constraints. And Kayak adaptively arbitrates between shipping data and shipping compute without knowing the underlying workload. So let's put the two approaches side by side. On the left, we have the ship data approach. On the right, we have the ship compute approach. And we combine these two approaches together. So now we have a storage server that exposes both the key value API and the RPC API. And then Kayak comes in to arbitrate between these two sets of execution schemes. And Kayak also applies adaptive rate limitation to try to ensure the latency target and still maximize the throughput. So the algorithm of Kayak is basically to tune two parameters. One is the request rate limitation, and the other is the fraction of requests to be executed using one or the other approach. And the challenges we face here is that there is no closed form expression of the relationship between the latency target and the request fraction configuration and the request rate. So this would also lead to difficulty in tuning these two parameters simultaneously, because we cannot use an analytical approach to solve this problem. And so what we decided to choose is we try to optimize these two parameters separately by using control loops. And so we have a rate limiting control loop, which tries to keep the latency within the latency target while still maximizing the throughput. And we have a request arbitration control loop, which tries to find the optimal fraction of requests to be executed using shipping data or shipping compute. And we combine these two control loops together to build a dual control loop design. So our solution is a dual control loop, and in our design, we explicitly put the rate limiting control loop before the request arbitration control loop. So the rate limiting control loop runs at a higher frequency than the request arbitration control loop. And this is because the other way around, as we have tested, is unstable. We have more details in the paper. And in the paper, we also proved that our control loop would achieve the optimal request rate and the fraction. So how does our system perform in real life? In our evaluation, we evaluate Kayak using a variety of workloads, and we evaluate Kayak against the state-of-the-art called ASFP. ASFP is very similar to Kayak. It also combines these two approaches together. However, a key difference is that in ASFP, it optimistically defaults to using RPC and reactively push back upon overloading. This will induce overhead when the storage server is overloaded. And so in the performance comparison, we measured the maximum achievable throughput at specific latency target, and we compare our system with the state of the art, and we outperform our baseline in all workloads. And the overall improvement is 12% to 60%. And we also observe that we have higher improvements with compute-intensive workloads. We also verify that our dual-loop control can converge to the optimal configuration. And in this experiment, we use a bimodal workload, which switches between a compute-intensive one and a less compute-intensive one with an interval of 5 seconds. And as you can see, when the workloads change, Kayak quickly converges to the optimal configuration. And we also verify that our system can ensure fairness when multiple tenants are contending for the storage server's computation resource. In this experiment, we run 4 tenants on 4 application servers. They are all sharing one single storage server. And the tenants are started one by one, and they are stopped one by one. So during this process, the tenants would join and leave, and we observe that the CPU resource on the storage server is fairly shared. And so in conclusion, Kayak is a system that proactively arbitrates between shipping data and shipping compute without workload knowledge. Kayak can maximize the throughput with latency as a low constraint, and Kayak ensures fairness across multiple tenants. Thank you.